Welcome to the video lecture on the area of a region between two curves. Recall that a definite integral from a to b of f of x dx finds the area under the curve f of x up until the x-axis over the bounds a to b. So we're going to use that to find the area between two curves. So suppose that we have a function f, which we're going to assume is greater than or equal to a second function g of x. So that means f of x is bigger or lies higher up than the graph of g on an interval a to b. What we want to find is the area between these two curves. So if we look at that area on the interval a to b, this function f is on top, the function g is on the bottom, and the area between them would be that shaded region right there. So the way that we're going to figure out what that area is we're going to take a look at first the area under f, which would be this area all the way down to the x-axis, and we can represent that with a definite integral from a to b of f of x dx. And then we can take from that the area under g, which is the lower curve, down to the x-axis, which would be this area right here, which is represented by the integral from a to b of g of x dx. And if you notice that this red area minus this blue area is exactly this area in between the two. So if I subtract these two integrals, that should give me the area between the two. And the way that we're going to represent that is also with a definite integral from a to b, but we're going to have inside of that integral the top function, which in this case is our f of x, minus our lower function, which in this case is the g of x. So you just want to do top minus bottom to make sure that you're getting a positive difference when you subtract. So the area between the two curves is the integral of the difference of the two functions over the bounds a to b. So that's what this theorem says right here. If f and g are continuous on the interval a to b, and g of x is less than or equal to f of x, so g is the lower one and f is the higher one, for all x in the interval a to b, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b is the definite integral from a to b of f of x minus g of x dx. And remember, this is always the top function minus the bottom function, and that's going to ensure that you get a positive area. So let's see some typical examples. The first one here says find the area between the function x squared plus 2x plus 1 and g of x equals 2x plus 5. So the key to these is always finding a good graph, and you can graph these by hand, or you may certainly use your graphing calculator to help you out. So if we pull up the calculator, I've typed into y1 the x squared plus 2x plus 1, and I've typed into y2 2x plus 5. So if I hit graph, that's what this graph is going to look like. We've got a parabola, and then we've got a line. So we're going to want to use that region in between, which is kind of this crescent shape right here, and find that area. Okay? So if we draw a sketch of that, we're going to have this region right here that we're looking for. Now the key to this is going to be recognizing, first of all, what function is on top and what function is on the bottom, so that we subtract top minus bottom. And in this picture with this region, we can see that the line is on the top and the parabola is on the bottom. So in terms of our integral, inside we're going to want to take the linear function, which is the 2x plus 5, and subtract from it the quadratic function. And when I subtract, I want to wrap it in parentheses because I want to subtract that entire function, that entire f, from this entire g. So that's what we would want to have inside of our integral. Now the other key thing that we need to find are our bounds, and you can either do that from your calculator using the intersect command, and that's perfectly fine, or you can find these algebraically as well. If you want to find the bounds algebraically, it's just the intersection points between these two curves. Where do these two curves equal each other? And since f of x is the same thing as y, and g of x is the same thing as y, then this is like saying, where are these two y values going to be equal? Well, that's going to happen when these two formulas are equal. So to find the intersection points algebraically or by hand, you would just set the two functions equal to each other and then solve. So to solve this, I'm going to get a 0 since this is a quadratic equation. If I subtract the 2x from both sides, then it cancels out. So I get an x squared plus 1 equals to 5. If I subtract the 1 over, I'm going to get x squared equals 4. And if I take the square root of both sides, that gives me a plus and a minus 2. So my bounds are negative 2 over here and positive 2 over here. So that's where this point is intersecting and this intersection point over here. Since this is an integral using x variables, you want to make sure that your bounds are x bounds as well, the way that x changes. And x changes from negative 2 up to positive 2. So those should be my two bounds that I use. So this would be our area integral for finding the area between these two curves. So now to actually evaluate this, I would recommend cleaning up what's inside of here first. So I'm going to go ahead and distribute my negative across and combine like terms. My two x's are going to cancel, and I'm going to get, whoops, I forgot to distribute my negative to that 1. Sorry about that. So this should be a minus 1. So 5 minus 1 will be 4, and we'll get that x squared as well with the negative in front. So what I want to integrate is 4 minus x squared. The antiderivative of 4 would just be 4x, and then the antiderivative of x squared, if you use your power rule, you add 1 to the power and you divide by the new power. So that would be x cubed over 3, and into that we're going to plug in our two bounds. So if I plug in 2, 4 times 2 is 8, minus 2 cubed is 8/3. I'm going to wrap that in parentheses, and then I'm going to subtract from that, wrapped in parentheses, the negative 2 plugged in. So 4 times negative 2 would be negative 8, minus negative 2 cubed stays negative, so this will be a negative 8 on top over 3. Minus minus becomes plus, so this is 8 minus 8/3. When I distribute my negative across, a minus minus becomes a plus, and this becomes a minus 8/3. 8 and 8 is 16. Negative 8 and negative 8 is negative 16/3. So that's going to be 48/3 minus 16/3. And when you subtract, you get 32/3. So this shaded area right here is 32/3. Okay? All right, let's try another one. This one says set up the area integral between f of x equals x minus 1 cubed and g of x equals x minus 1. So here we don't actually need to compute the area, but we do need to set it up and write down what that area integral would look like. So we're going to start by graphing this on our calculator and visualizing what region it is that we're talking about. So on my calculator, I have typed in my x minus 1 quantity cubed in y1 and x minus 1 in y2, and I needed to adjust my window so that we could see this very clearly. So I sort of zoomed in. My y bounds were negative 2 to 2, my x bounds were negative 1 to 5, and this gives you a much clearer, more zoomed in picture of what's going on. So we've got this cubic function, and then we've got this line sort of intersecting right through the middle of it. Now what's going to make this particular example a little bit tricky is noticing what happens in terms of the top function versus the bottom function. On this smaller region over here below the x-axis, the cubic function, the curvy part, is what's on top, and the line is what's on the bottom. But then when we get past this intersection point in the middle, we switch so that the line is on top and then the curvy part, the cubic, is on the bottom. And that means because that changes, we're going to need two different integrals. The first integral will be when the cubic is on top with the appropriate bounds for when that happens, versus the second integral, which will have the line on top over the bounds where that occurs. So let's draw this picture and find our intersection points. And you can find those intersection points by using the intersect command under calc right here, that's perfectly okay, but I'm going to show you how to do it algebraically as well. So our picture looked something kind of like this. Okay, so we have an intersection point here, here, and here. So we have 3 intersection points. So to find them, we would want to set these 2 equations equal to each other. So the cubic equal to the line. And to solve this, I'm just going to be a little bit creative in how I factor this. I'm going to take this x minus 1 and I'm going to subtract it all using parentheses over to the left side. So I subtracted this entire quantity to the left side and left that minus sign out front. And that way I can think of this x minus 1 as like a GCF. So if I factor out a GCF of x minus 1, from this cubic term I'm going to have 2 of them left, and from this linear factor I'm just going to have a factor of 1 left. If you were to redistribute, you would get back this initial expression. So now if I go ahead and look at what's on the inside of these brackets, this becomes a difference of squares. So I've got a quantity squared minus another square. So this factors some more. I'm going to need an x minus 1 and an x minus 1 to get x minus 1 squared. I'm going to need a 1 and a 1 to get a 1, and one of these should be plus and one of these should be minus, so that I get that difference of squares pattern with no middle term. And then finally, if I go ahead and simplify, x minus 1 plus 1 is just an x, and x minus 1 minus 1 is an x minus 2. So that tells me that my solutions are going to be 1 from this first factor, 0 from the second factor, and 2 from the third factor. So this is at 0, this is at 1, and this is at 2. So again, that was just me being clever, algebraically solving this. If you prefer to use that intersect command, that is fine too. Okay? So now that we have our intersection points, we're ready to set up our integral. And remember, we're actually going to need 2, because on the interval from 0 to 1, right in the middle, it's the cubic function that is on top. So that first integral with bounds from 0 to 1 should be the cubic function first on top minus the linear function on the bottom. And then we're going to add to that the second integral, which will go from 1 to 2, and that has the line on top, so the x minus 1, and then we're going to subtract from that the cubic function, which is now on the bottom. So there are my 2 integrals that I would need. Solve each one, and then we would have the actual area. But this one only required that we set it up. Okay? All right, let's take a look at another example. We've got y equals x squared and y equals 6 minus x, and we want to set up the area integral between these 2 curves. So this one is easy enough that I can just graph it by hand, but you could also use a calculator. Y equals x squared is just a nice parabola, and 6 minus x is a linear function with an x-intercept at 6, and it's going to have a negative slope, so it would look something like that. So we're talking about this region right here. So on top, what we have is this line. So we're going to use the 6 minus x on the top coming first, and then we're going to subtract from it the parabola on the bottom, which would be the x squared. So this is going to be 6 minus x squared, and we need to know our bounds, and we've got 2 intersection points here and here. So to find those, I'm just going to set my 2 equations equal to each other. I'm going to set x squared equal to 6 minus x. Again, this is a quadratic equation, so I'm going to add the x to the left side and subtract the 6 to the left side, and then this will factor. And we'll get x and x, 3 and 2. I need the 3 to be plus and the 2 to be minus, so that I get a minus 6 and a plus 1 in the middle. So I get negative 3 and positive 2. So that means this bound here is a negative 3, and this bound over here is a 2. Those are my x's. So my bounds should be negative 3. You always want your lower bound or your leftmost bound on the bottom up to the 2. Okay? So there's my integral. 6 minus x squared dx from negative 3 to 2. Okay, the next one. Set up the area integral of the region between f of x equals sine x and g of x equals cosine 2x from minus pi over 2 to positive pi over 2. So first we need to get a graph of this, and I'm going to do this on my calculator because this one is not as easy to do by hand. So we're going to pull up the calculator and take a look at what this is going to have as our area region. So I've got sine of x in y1 and cosine of 2x in y2. And again, I adjusted my window dimensions to make this look good. Since we're only looking at this from minus pi over 2 to pi over 2 for the x's, that's what I set my x bounds to be. And then for my y's, I just went from negative 2 to 2. So here's my sine curve, and then here's that cosine of 2x. Okay, so we've got our two different curves, and we want to figure out the region that we're talking about here. So we've got this region obviously in between our two curves on the left here, but we want to go all the way from minus pi over 2 up to pi over 2. So we want to go all the way over to this vertical line here that would be at pi over 2 for x. And so we also want to find this area on this side as well, which means you want to look at what's on top and what's on bottom. Over here, this curve on top is your cosine curve, cosine of 2x. So on top we want cosine, and on the bottom we want sine when we're in this first region. But then it's going to switch after we get to this middle intersection point, and then our sine is going to be on top and our cosine is going to be on the bottom. So let's draw a rough sketch of this, and then we'll find those intersection points. So our graph is going to look something like this. Our sine curve from minus pi over 2 to pi over 2 looks kind of like that. And then our cosine of 2x looked something like this. Okay? So the intersection points, there was one right here, there's one in the middle, and then over here on the right, we don't really have an intersection point, but we're going to use that right bound of pi over 2 as kind of an intersection point. So we're going to stop once we get to that pi over 2. So over here, we've got the blue curve, the cosine on top, and the sine curve, the black one on the bottom. And then once we hit this middle point, then it switches. The sine is on top and the cosine is on the bottom. So let's go ahead and find those intersection points first. So I'm going to set my two functions, sine x and cosine 2x, equal to each other. And to solve this algebraically, you are going to need to use some identities. I don't like that cosine of 2x in there because it has that double angle, so I'm going to use a double angle identity. And since this is just a sine x on the left side, I'm going to use the double angle identity for cosine that uses only sines. So I'm going to leave the sine x the way it is, and cosine of 2x is the same as 1 minus 2 sine squared x. And now I have a quadratic equation only in terms of sines. Let's go ahead and add that 2 sine squared x to the left side, and let's subtract the 1, and this is now something that can factor. I can have a 2 sine x and a sine x to get 2 sine squared x, a 1 and a 1, and if I make the plus be on the second factor and the minus on the first factor, then I'll get a positive 1 in the middle. So then if I set each of these to 0, 2 sine x will equal to 1 when sine x equals to a half, and that happens on this region when sine is equal to pi over 6. So that's this one right here. And then sine of x will equal to negative 1 when x is negative pi over 2, and that's this intersection point right here. So those are my two intersection points. There isn't an intersection point over here, but we're going to stop once we hit pi over 2. So let's take a look first at this first region here. And what I like to do, and this is something we're going to get into a lot when we do volumes, is I like to draw in a little slice. Suppose that I took a little rectangular slice and wanted to find the area of that rectangle. Well, I would need to know its height, and on the top would be this blue curve, which is that cosine 2x, and on the bottom would be that sine curve. So that's how I know that for this first integral, I want to do the blue curve, which is the cosine 2x first, because that's on top, minus the black curve on the bottom, which was the sine of x. And we want to use that just from negative pi over 2 until pi over 6. So that will get me this whole area right here. Now if I switch to the other piece and draw in one little slice right here, now on top is the black curve, which is the sine, and on the bottom is the cosine. So for this second integral, I want to start with the sine of x first on top, minus the cosine of 2x on the bottom. And I'm going to do that from pi over 6 until pi over 2. And if I add these two together, then that gives me that entire area from minus pi over 2 up to pi over 2. And that gives me this second little region right here. So the two added together give me the whole area. Okay? All right, next example. Find the area of the region bounded by the function g of x equals 4 over 2 minus x, y equals to 4, and x equals to 0. So on the calculator, I've got 4 over 2 minus x. Make sure you're using parentheses around that 2 minus x when you type it into your calculator. And then I typed in y equals to 4 into my y sub 2. And we can't really graph x equals to 0 using this screen because that's a vertical line, which means it's not a function. So you just have to visualize that on your own. So I'm just typing in the two equations that were equal to y. And then I'm going to graph this, and I adjusted my window slightly. I have x going from negative 3 up to 5, and then I have my y's going from negative 5 up to 5. So that 4 over 2 minus x, that's this reciprocal function here, and then my y equals to 4 is just this horizontal line going across. So what region is bounded by this curvy function, this horizontal line going across, and also x equals 0, which is the vertical line through 0, which would also be known as the y-axis. So what region is bounded by this y-axis, this horizontal line going across, and the curve? Well, that's this almost triangular region right here. So that's the region that we're trying to find the area of. Okay, so let's sketch that and set up our integral. So my region is looking something like this. Right here. Okay, so this is at a height of 4, and then this is that curve 4 over 2 minus x. So if I wanted to find out some intersection points, like right here, we would want to take our two curves, 4 over 2 minus x and y equals to 4, and find out where those two curves intersect. So we could set 4 over 2 minus x equal to 4. And to solve this algebraically, you can just think of this 4 as being 4 over 1 and cross multiply. Or in other words, just multiply through by that denominator 2 minus x. Okay? So it's going to cancel out on the left side, giving me just 4. And on the right side, when I distribute that 4 across, we'll get 8 minus 4x. So if I subtract the 8 over, we get negative 4 equals negative 4x. So when I divide by negative 4, that means x is 1. So this is intersecting at 1. So we've got our 0 on the left bound, and then we've got this 1 on the right. So those are going to be my bounds for x's. Now remember, draw in a little slice, a little rectangular slice. And if I draw that, what is on the top of that slice? That's this horizontal line, y equals to 4. And then what's on the bottom of that slice, that's this curve, which has the equation 4 over 2 minus x. So in terms of our integral, the 4, the horizontal line was on top, so that comes first, minus the curve on the bottom, so that comes second. So that's what we want to integrate. And our bounds, we just found out, were from 0, that y-axis, up until 1, which is where they intersect. So from 0 to 1. Now this one asks us to actually find the area, so let's go ahead and integrate this. The antiderivative of 4 would just be 4x. The second integral is a little bit trickier to do, so what I'm going to do is break it up, and I'm going to go ahead and write it this way temporarily. And this 4 on top really isn't doing me any good, so it's a constant, which means I can pull it out. So let's go ahead and pull it out front of my integral. And let's look at what we have here. We have 1 over 2 minus x. And that's a fraction. And whenever I see fractions and I'm thinking in terms of integrals or antiderivatives, I always immediately think of the possibility of an ln. And if this is going to be an ln, then I need to see inside of my integral stuff prime over stuff. And that is almost what I have. The derivative of this denominator would be a -1, and I have a +1 on top. So I can fix that by putting a negative in the top and counterbalancing by a negative out front, which is just going to cancel out this minus that I already had and turn it into a plus. So now this is stuff prime over stuff, and the antiderivative of that is the ln of the stuff, the ln of the denominator. So this will be the ln of the absolute value of that denominator, 2 minus x, and this 4 will stay out front. So the derivative of 4 ln of 2 minus x is 4 times -1 over 2 minus x. That's why it works. Okay? So now that we have our antiderivative, let's use our bounds and plug them in. So if I plug in 1, 4 times 1 is 4. Then I'm going to get 4 times the ln of 2 minus 1 is 1. So this will be the ln of 1. And then I want to subtract from that the 0 plugged in. 4 times 0 stays 0. And then this will be 4 times the ln of 2 minus 0 is 2. And the absolute value of 2 is +2. So I don't need those absolute values anymore. The ln of 1 is 0. So this gives me 4 minus, this goes away, 4 ln of 2. And my final answer here is going to be 4 minus 4 ln 2. Okay, next example. Find the area of the region bounded by f of y equals y squared plus 1, g of y equals to 0, y equals -1, and y equals to 2. So this problem is a little bit different because instead of your normal function notation, which we're used to seeing as f of x equals something in terms of x, now we have f of y is equal to y squared plus 1, for example. So this time our our dependent variable is that y, and we're going to think of this sort of in a different notation. So instead of replacing this f of x with a y, we're going to replace f of y with an x. So this is really the same as saying x equals y squared plus 1. And instead of saying g of y, we can call that an x and think of this as x is equal to 0. And then we have these other two horizontal lines at y equals -1 and y equals +2. So it's slightly different notation. This time we're going to be graphing these thinking in terms of a function of y instead of a function of x. So how would you graph x equals y squared plus 1? We can't really type that into our graphing calculator because the variables are switched around here. So this one we're going to do by hand. And what you want to realize is that because our variables are switched around and it's the y that's being squared instead of the x that's being squared, it's still a parabola, but it's a sideways parabola. So this is going to be a parabola on its side. And if you think about some of the intercepts here. If y is 0, if I plug in a 0, then that means x would be 1. So this is going to hit right at 1 on the x-axis. And because the y squared term is positive, this is going to be a parabola that points to the right. So it's going to be a parabola that does something like this. Now, if you really did not know how to do that, you could solve this for y by subtracting 1, taking a square root, and making sure that you do a plus and a minus. The plus square root case would give you this top half of the sideways parabola, and the minus square root case would give you the lower half. And you could graph those on your calculator using y1 as the positive square root of x minus 1 and y2 as the negative square root of x minus 1. And that way you would get the full sideways parabola. Okay, so it is possible to do it on your calculator as well. Now x equals to 0, that's a vertical line through 0, which is just our y-axis, so that would be this right here. Y equals negative 1 is a horizontal line at a height of negative 1. And y equals 2 is a horizontal line at a height of 2. So what region are we talking about that is bounded by this parabola, by the vertical line x equals 0, and between negative 1 and 2 for the y? Well, we're talking about this region right here. It almost looks kind of like the state of Minnesota in terms of its shape. Okay? So when we talk about that shape, normally in all the other examples that we've been doing, we've been thinking in terms of top function minus bottom function. And that gets a little bit tricky to do here, because if you look at this region, I'm going to kind of blow it up here a little bit. We've got this sort of shape going on. Over here, if I were to draw a slice, what's on top would be this height 2, and what's on bottom would be that height negative 1. But when I go over here, what's on top is this 2, and what's on the bottom is this curve. And if I come down here, on top I'm on that curve, and on the bottom I'm at negative 1. So there's a lot of changes going on in terms of what's on top and what's on bottom, and for each change you would need a new integral to do. So that makes this kind of tricky in terms of top minus bottom. So trying to do top minus bottom in this example would result in several integrals, one for each change. So as an alternative to that, instead of going top minus bottom, we're going to go left and right. We're going to go sideways. So instead of drawing my slices up and down, let's draw our slices horizontally. So suppose I look at that slice. What curve is on the right? Well, that would be the parabola. And what curve is on the left? Well, that's the y-axis. What happens if I draw a slice over here? Same thing, parabola on the right, y-axis on the left. If I draw my slice down here, parabola on the right, y-axis on the left. If I do it down here, parabola on the right, y-axis on the left. So it's consistently the same thing each time. And that's good news for us, because if it's always the same on the right and on the left, that means we only need one integral in order to do this. So instead of going top minus bottom, we are going to go right minus left. And this will be a dy integral because these slices are going horizontally along that y-axis, and then the bounds that we use are going to be y bounds. Not how x changes, but how y changes. So for this example, we want to go as low as y equals negative 1 up until y equals to 2. So our bounds are going to be from negative 1 up to 2. So let's write out what this integral becomes. It's going to be negative 1 up to 2, and then the curve on the right was this parabola, which has as its equation or its formula y squared plus 1. So that's the right curve. And then I'm going to subtract from that the curve that's on the left, which was this y-axis, which is just x equals to 0. So that's our dy integral, where we're thinking horizontally instead of vertically. So in order to actually integrate this, this is just the integral of y squared plus 1 dy. And everything in here is in terms of y's, the formula, the dy, and the bounds. So to integrate, this just becomes y cubed over 3 plus y. If I plug in 2 cubed is 8, so this is 8/3 plus 2. If I plug in -1 cubed stays negative, so this is -1/3 minus 1. And if we simplify that, we're going to get an 8/3 minus a -1/3, which becomes 8/3 plus 1/3, which is 9/3 or 3. And then we're going to get a 2 minus a -1, which becomes 2 plus 1, which is another 3. So this is just 6. Okay, so when you're talking about examples where, and this usually happens when you have curves that are going sideways, like our sideways parabolas, typically you want to think in terms of right minus left instead of top minus bottom, because it'll be easier to set up the integral and you'll only have to use one integral instead of several. So you always want to do the right curve minus the left curve. That way you're getting that positive difference. You want to do the bigger curve on the right first minus the smaller curve on the left second. That way you'll get a positive answer. And typically you're using these when it's these sideways parabolas, and I like to encourage you to draw in these little slices to guarantee that you're always on the same curve on the right side and on the same curve on the left side, so that you're consistently using the same right minus left. Otherwise you'd have to use several different integrals. Okay, let's try another example like this. Find the area of the region bounded by the curves x equals -y squared plus 2y and x equals -y. So let's go ahead and graph this. Now to graph this x equals -y squared plus 2y, a couple of things here. It's a quadratic, but it's in terms of y, so that means it's going to be another sideways parabola. Since the leading term, the y squared term, is negative, this time it's going to point to the left instead of pointing to the right like the last example did. And what I like to do to help place this is find some of the intercepts. So what you could notice here is if you pulled out a y, you would be left with a -y plus 2. So if you set x equal to 0, that means we're going to have y-intercepts at 0 for this factor, and -y plus 2 equals to 0 at positive 2. So we have two y-intercepts at 0 and 2. So here and here is where it's going to cross that y-axis. And as I said before, because the y squared term is negative, that means this is going to point to the left. So it's going to open up towards the left and look something like this. And we just kind of need a rough sketch. It doesn't need to be perfect. You just need to know the general shape. Now the line x equals -y is the same as -x equals to y. So that's just a line with a y-intercept of 0 because there's no b, and the slope is -1. So it's going to be a line that looks just like that. So there's my two curves. Now, because it's this sideways parabola, most likely we're going to want to do those horizontal slices. So let's draw a few of them in to make sure that we're consistently the same on the right and on the left. So if I draw one in over here, on the right I'm on the parabola, on the left I'm on the line. If I were to draw it down here, on the right I'm on the parabola, on the left I'm on the line, and down here on the right I'm on the parabola, and on the left I'm on the line. So consistently I'm always the same, which means I only need one integral. And that integral is going to be the right curve, which is this parabola, and I'm going to use it in terms of y's. Whenever you go horizontally like this, you should expect to see y variables inside of your integral. So that's the right, and then we're going to subtract from that the left, and the left is this line right here, which has x equal to -y as its formula. So that's what we're going to be integrating. The next thing we need to know are the bounds. And because this is a y integral, we want to use y bounds. So we need to know how low and how high this should be integrated. And it's going to be based on our intersection points. Now this intersection point down here is obviously at the origin, but there's another intersection point up here which it's not so obvious how high that is. So to find out what the intersection points are, we're just going to set this x equals equation equal to this x equals equation. So we're going to set the negative y squared plus 2y equal to the negative y. And I don't like having a leading negative term, so I'm going to go ahead and add the y squared over to the right side to make it positive. And when I subtract this 2y, that makes this become minus 3y. So if I pull out a y, then that means I have intersection points at 0 and 3 for the y. So that means this height right here is 3, and this height right here is 0. Okay? So my bounds then are going to be 0 up until this height right here, which is at a height of 3. So my integral, when I clean this up a little bit, minus minus becomes plus. So this is negative y squared plus 3y dy from 0 to 3. And now to integrate it, the integral of y squared becomes y cubed over 3, but there's that minus in front. The integral of y becomes y squared over 2, and that 3 stays in front. And I want to do this from 0 to 3. So if I plug in 3 cubed is 27. 27 divided by 3 is 9. So this will be negative 9 plus 3 times 3 squared is again that 27, but this time it's over 2. And then I want to subtract from that 0 plugged in for both of these, and that's going to make both of these 0. So this will be negative 18 halves plus 27 halves, which is 9 halves. So that's this area right here. Okay? All right, the next example is a little bit different. Here we want to find b such that the line y equals to b divides the region bounded by the graphs of the equations listed into two regions of equal area. So the region that I'm talking about here is y equals 9 minus the square root of x, y equals to 0, and x equals to 0. So to graph this, you can use your calculator, type in 9 minus square root of x, and I'm just going to do a standard window, and it looks like your square root curve shifted up 9 units and flipped over, so it's going to be upside down. So there's my graph. So if I replicate that graph, it's going to look like the square root curve pushed up 9 units and then flipped over. So it's going to look something like this. It's a very slow graph, but eventually it will eventually hit the x-axis and cross and keep going down below. So my graph would look something like that. And then I also have as a bound y equals to 0, which is a horizontal line right through the x-axis. So it looks like that. And then x equals 0 is this vertical line. And that's the original region that we're talking about, bounded by these three curves. So in this first quadrant, this little region right here. So now what we want to do with this is we want to divide it into two regions of equal area using this line y equals to b. So there's some line y equals b, that's just a horizontal line at a height of b. There's some line that's going to cut this in half so that this top region up here has the same area as this bottom region. Okay, and we want to find where that dividing point is going to be. So in order to set this up, what we're going to notice is that we want this top area to be the same as this bottom area. So I'm going to set up an integral that represents this top region, and then I'm going to set up an integral that represents this bottom region, and then I'm going to set the two equal to each other. Now, if you think of this in terms of vertical slices, then we're going to have a little bit of a problem, because up here on top, it's not so bad. We would have on top that square root curve, and on the bottom would be that height b. On top the curve, on the bottom b, on top the curve, on the bottom b. So that's nice and consistent. However, on the bottom region, on the top over here is that horizontal line B, and on the bottom is just the x-axis. Same goes here, same goes here. But as soon as I get over here, on the top now I'm on the curve, and on the bottom I'm at 0. Top I'm at the curve, and on the bottom I'm at 0. So there's a switch. Here to the left of this intersection point, I'm at B on top and 0 on the bottom. To the right of that intersection point, I'm on the curve on top and at 0 on the bottom. So that would require two different integrals, which is certainly doable, but potentially we could make our life easier if we go horizontally instead. So what I'm going to do is see what happens if we draw our sketch so that we go horizontally across. So if I take a slice this way, on the right I'm on the curve, on the left the y-axis. On the right I'm on the curve, on the left the y-axis. So that looks pretty consistent. Over here, if I draw a slice, on the right I'm on the curve, on the left the x-axis. On the right I'm on the curve, on the left the x-axis, and then all the way down here, that little slice, on the right I'm on the curve, and on the left I'm on the y-axis. So it was consistently the right being the curve and the left being the x-axis, so I would only need one integral for each of these two regions. So I'm going to choose to do this using right minus left instead of top minus bottom, so that I only have to do one integral for each region. Okay, so let's do the top area first, this area right here. So on the right, we were on this curve, and on the left, we were on that y-axis. Now, because we're going right to left, remember when you go right to left, you want y integrals. You want a dy integral. So I need to know what this curve is in terms of y. So I need to take this curve and I need to solve it for x in terms of y, so that I get a formula not involving x's, but a formula involving y's. So how could I do that? Well, first thing I could do is I'm going to add the square root of x over to the left side, and I'm going to subtract the y over to the right side. And then I'm going to square both sides. So this square root function is very similar to this equation right here in terms of y's. So I'm going to use that instead. So on the right would be this curve in terms of y, which is this 9 minus y quantity squared. And on the left is just our bounds here, and the bound on the left is actually this vertical line, which is when x is 0. So what we're really doing when we do right minus left is we're taking this x minus this x. So this x coordinate minus this x coordinate, which is always 0. So on the right, our x value in terms of y is this function right here, and on the left, x is always 0. So this is right minus left. And for this top region, what would our bounds be? How does y vary? Well, y starts at a height of b, and it goes up to this intercept, which we knew was at 9. So the bounds for this upper region would be from b up to 9. So that's the top half. What we want is that area to equal the area of this bottom half down here. So what would that integral be? Well, again, on the right, it's always on this curve, which in terms of y's is 9 minus y quantity squared. And on the left, it's always that y-axis, which is when x is 0. So that part of the integral is the same, but the bounds are different. This time, the bounds for y start at a height of 0 and go up to b. So here my bounds would be from 0 to b. So we want this top area to equal this bottom area, and we're going to set them equal to each other and figure out what that b would have to equal. Now, how do you integrate 9 minus y quantity squared? There's the easy way, and then there's the hard way. The hard way would be to expand this all out, FOIL it all out, and then integrate term by term. The easy way to integrate it is to recognize this as pattern recognition. You have your inside function, I'll call that f, and, I'm going to call that inside function g, that's how we've done it in the past. And the outer function is my f, that's the square. And in order for pattern recognition to work, you need to have your outer function f, your inner function g, and you also need to have present the derivative of your inner function. So we need a g prime in here as well. And what would g prime equal? What's the derivative of 9 minus y? Just a -1, which I don't have, but I can easily put it in. Let's put it in right there. So there I have my g prime, and I counterbalance by a negative. So that minus out front stays put, and since I have f, g, and g prime all present inside of the integral, then pattern recognition says the only piece of this that you actually integrate is this outer function f. And to integrate a square, that becomes a cube over 3. And what was inside stays put. And that's exactly what this integral is going to be as well on the right-hand side, because it's exactly the same function that we're integrating on both sides. We just have different bounds. So this integral here will also be a negative put in and a negative counterbalanced, and then it would become -9 minus y quantity cubed over 3. The only difference between the left and the right side is that on the left side we're going from b to 9, and on the right side we're going from 0 to b. So if I plug in 9 minus 9 becomes 0, so this whole top bound becomes 0. When I plug in b, I'm going to get a minus because we're subtracting top minus bottom, and then I'm also going to get this minus still present, and this becomes 9 minus b quantity cubed over 3. Minus minus becomes plus. On the right side, when I plug in b, we're going to get -9 minus b quantity cubed over 3 minus, now I need to plug in 0. When I plug in 0, I get this negative out front still there, and 9 minus 0 stays 9, so this is 9 cubed over 3. Minus minus becomes plus. Okay, so looks kind of messy. Let's see what we have. We've got a 9 minus b cubed over 3 on the left, a -9 minus b cubed over 3 on the right, and 9 cubed over 3 reduces to 243, and it's positive. So what I'm going to do is I'm going to add this entire fraction over to the other side. And that makes it cancel out on the right side, just giving me that 243. And since these fractions are the same, 1 plus 1 makes 2 of them, so this is going to be 2 of these 9 minus b cubes over 3. Next thing I'm going to do is I'm going to get rid of this fraction by multiplying by the reciprocal. So I'm going to multiply both sides by 3/2, so that'll just give me 9 minus b quantity cubed. And 243 times 3 is 729 over that 2. Now I'm going to undo the cube by taking a cube root of both sides. So I get 9 minus b by itself. And the cube root of 729 is just 9. And on the bottom I'll get cube root of 2. If I subtract 9 from both sides, I get negative b equals 9 over cube root of 2 minus 9. And finally, I'm going to switch all my signs to get a positive b. And when I switch the signs, I'm going to also switch the order. So instead of having a negative 9, this becomes a positive 9. And then instead of having a positive 9 over cube root of 3, 9 over cube root of 2, it becomes a negative 9 over cube root of 2. As a decimal, that's approximately 1.857. So that means that we would need to draw a horizontal line at about 1.857, so actually really close to that x-axis down here, in order for the top area and the bottom area to be equal. Now it's because this extends out really, really far, and you get a lot of extra area going out to the right. So this horizontal line needs to be low to counterbalance all that area that we're going to get off to the right-hand side. Okay, so the dividing line needs to be approximately 1.857. Okay? All right, that one had a bit of yucky algebra involved in it, but all doable. You just have to be patient. Okay, last example. A state legislator is debating two proposals for eliminating the annual budget deficits by the year 2010. The rate of decrease for each proposal is shown in the figure. From the viewpoint of minimizing the cumulative federal deficit, which is the better proposal? So again, we have these two proposals. The black one is this concave down shape, and then proposal 2 is this concave up shape. And we want to know whether or not we should go with proposal 1 or proposal 2. And these proposals are showing the rate of decrease of this annual budget deficit. So how could we decide which of these two proposals to go with in terms of minimizing this cumulative federal deficit? Remember that these curves represent the rate of decrease. So what happens when you integrate a rate? You end up with a cumulative or total amount. So when you integrate a rate, you get a total amount. So if we're integrating a rate of decrease of this budget deficit, then we're going to end up with, when we integrate it, the total amount of that deficit. And we want to minimize that. So which of these is going to have a smaller integral? And remember that an integral means area under the curve. So if you look at proposal 1 versus proposal 2, which one of those proposals has a smaller area underneath? Well, that would be the proposal 2 because it's concave up, and its area would just be this area here versus proposal 1, which would be larger than that. So proposal 2 has less area under the curve, which means when you integrate it, that means it's going to give us less total deficit. And since we want to minimize the deficit, then we want to go with proposal 2. Because it will cut that deficit faster than proposal 1. Whoops. Sorry, my pen is going kind of crazy today. So we want to go with proposal 2 because it cuts the deficit faster than proposal 1. Okay? All right, that concludes our video lecture on area between two curves. Good luck.